So from the homework number 11, you have this vector that's equal to xy for the x component and xy squared for the, x and y, whatever. We don't know what this vector is. We don't know what these variables mean. You know, I'm used to calling this the x and y components, but we don't know that those are necessarily x and y positions or anything. They're just variables. But we're trying to come up with an expression for du dt. So we're trying to find du dt. Another name for that is u dot. So always remember that's what the dot means. You're going to see that all the time in this class. And we want to do it in terms of x, y, x dot, and y dot. Okay. So let's break it up into two pieces. So first, xy, if you're taking the time derivative of this, you could also write that as xy time derivative of the whole thing. That's just another way of writing the same thing. And we have to use the product rule for this. So this is going to be, you can think of this as d dt of x times y plus x times d dt of y. And we can see from what we're given above that dx dt, we're just going to call that x dot. We're saying we know that. dy dt, we're going to call y dot. So now we can write this as x dot y plus x y dot. So that's it for the first component. Anybody have any questions about that? And then for the second component, so we want d dt of xy squared. So that y squared is going to mean we're going to have to use a chain rule. So you can think of this as, so first I'm going to use the product rule. So we have d dt of x times y squared plus x times d dt of y squared. That's what the product rule says. Okay. But this is the first time that, so dx dt, we have a name for that. We were given a name for that. We're calling that x dot. Okay. But we don't have a name for dy squared dt. So for that one, we're going to have to use the chain rule. Okay. So I'm going to write this as, we can write this first one as x dot y squared. But this second term, I'm going to write that as x times, so how are we going to express this dy squared dt? I can write that as d of y squared dy times dy dt. That's the chain rule. Okay? You with me on that? And so this is x dot y squared plus x. Dy squared dy, you know that that's 2y. Dy dt, we have a name for that. And so this comes out to be x dot y squared plus 2xy y dot. Now we can just put the whole thing together into a vector form. So u dot is equal to x dot y plus xy dot. And the second component is x dot y squared plus 2xy y dot. Any questions about that? I think it's a good exercise. Like, I think sometimes you get in the bad habit with derivatives and integrals and stuff of just like writing stuff down. Like, you've done it so many times, you just write stuff down and then you're like, I don't know, it looks like it might be right. And then you just move on. But it's a good habit to get into, to every step think like, do I know why I'm doing this? You know, break it down into these individual steps. Like here, I broke it down into product rule first, and then I saw that I was going to have to use the chain rule for one of these things that we're multiplying, you know. Okay. So now we're going to go on to solving ordinary differential equations. So solving ordinary differential equations using separation of variables. An ordinary differential equation is one where there is only one independent variable. Another way to think of that is that the derivatives are only with respect to a single variable. And that means that there are no partial derivatives. And your goal for an ordinary differential equation is find one or more dependent variables as a function of the single independent variable. Okay, so for example, if you have this differential equation, y double prime plus 10 y prime. I don't know why I'm using that prime notation. This is like, erase that. I'm going to try the rest of this class not to use that prime notation because the d whatever notation and the dot notation, those are like very specific about what you're doing, you know? You know exactly what you're taking the derivative of, you know exactly what you're taking the derivative with respect to. That prime notation is like, I don't know, just take a derivative. But we have to be careful, really careful about that, you know? Taking the derivative with respect to y is not the same as taking the derivative with respect to t. So I'm not gonna write that prime notation. So let's say we got d squared y dx squared plus 10 dy dx. plus dy dx times y squared is equal to 50x. Well, let's identify the dependent and independent variables, and you can do that from the derivatives. Since we're taking all of our derivatives are of y with respect to x, we can say that the independent variable is x. In this case, there's only one dependent variable, but we'll see them where we have more than those eventually. Our dependent variable is y, and so that means our goal is to find y as a function of x. Okay, so y is equal to cosine of 1/2 x, whatever, you know. We're trying to find that function. Okay, we're not trying to find a single value of y or anything like that. We're trying to find a function. Okay? And we're only going to see ordinary differential equations that you can solve by separation of variables.
The question will just be let's solve this.
Yeah, that's right. That's right. Actually, I think maybe some of the questions do ask you to identify independent and dependent first. You know, if you're not doing that in your head, then before you start anyways, then that's a problem, you know. So get in the habit of first just centering yourself on what you're trying to do. But yeah, it's just asking you to solve it. Okay, so separation of variables. So you can do this anytime you have a problem of this form. And obviously these variables are just totally arbitrary, but I'm going to say dy ds is equal to some function of the dependent variable times some function of the independent variable. And obviously you could write this the same way as, let's call it capital F of y times capital G function of s dy ds is equal to 1. That, you know, that means the same thing because 1 over these functions is also a function, you know. You might have to deal with some zeros, some places where it becomes undefined, but there'll just be a finite number of those you can deal with. So these are basically the same thing. So S is the independent variable, and Y is the dependent variable, which means that we want to find y as a function of s. And so what we're going to do is get all the y stuff on one side, all the s stuff on the other side. Let's say get all the dependent variable stuff on one side, get all the independent variable stuff on the other side. So I'm going to think of it this way. So I'm going to split up that derivative. So I'm going to have, let's first go dy is equal to f of y times g of s ds, and then divide the function of y, where is that? Yeah. Divide f of y from both sides, so you get dy over f of y is equal to g of s ds. And now you have two things that you can integrate. Okay, bless you. One thing to keep in mind here is every time you integrate both sides, you're going to get a constant of integration. And you're going to have to solve for that using what are called boundary conditions. So every time you integrate both sides, you're going to get an unknown constant of integration. And you're going to solve for that using a boundary condition. In other words, the problem has to be given to you with one boundary condition per integration step, okay? So the problem needs to provide one boundary condition per integration step. Well, if your differential equation is a first order differential equation, the highest derivative is a first derivative, then you need one boundary condition. Every order of derivative that's given requires a new boundary condition. So if your highest derivative is a fourth order derivative, then you're going to need 4 boundary conditions. Okay, so it's pretty simple. Okay. You need n boundary conditions for an nth order derivative. I'm starting out with just first order problems, but we'll get on to those. So let's do an example. Let's say that we have a differential equation. Y dot is equal to y squared times t squared where y, when time is equal to 0, y is equal to 10. Okay? At time 0, y is equal to 10. And we just want to solve this differential equation. Okay, so first of all, what does solving it mean? What's our independent variable? T, yep, that's right. And our dependent variable? Right. And so that says we're looking for a function, y is a function of time. Okay, so I'm going to rewrite this as dy dt is equal to y squared t squared. And so if I get all the y stuff on the left side, all the t stuff on the right side, we have y to the negative second power dy is equal to t squared dt. Integrate both sides, and you get negative y over, well, you get y to the negative 1 over negative 1, so you get this, is equal to t cubed over 3 plus a constant of integration. I added, we have a constant of integration from both sides. I just lump them into a single thing that I'll call c. Okay? Any questions about that step? But now we have to figure out what that c is. So first of all, are we given enough boundary conditions to solve it? Yeah, we have a first order derivative and we have one boundary condition, so that should be perfect. Okay, so what I'm going to do is I'm going to set y equal to 10 and t equal to 0. That's what the boundary condition says, that those have to occur at the same state. Are you with me on that? So I'm going to go negative 10 to the minus 1 is equal to 0 cubed over 3 plus c. So we have c is equal to negative 0.1. And now we can update this thing. Okay, so we know that negative y to the negative 1 is equal to t cubed over 3 minus 0.1. Now y to the negative 1 is equal to, I'll write it as 0.1 minus t cubed over 3. And now take the reciprocal of both sides. Y is equal to, so I'm going to rewrite this as 0.3 over 3 minus t cubed, like that. And so y is equal to 3 over 0.3 minus t cubed. And that's your function well, that's a pretty weird way to reduce that fraction. So let's call it 30 over 3 minus 10t cubed, but that's how to do it. Yeah?
Do you want us to always simplify down to y or variable?
Oh, yeah, instead of just ending at this point here.
Yeah.
I think I will tell you that in the question. I think some problems don't say that specifically, and you can skip that. But any other questions? Okay, I want you to notice one other thing here. This approach also works for, I'll basically, what I'm going to be getting at here is, so this is what's required to use separation of variables. Well, that function f or that function g could just be 1, And so you can use this for You can also use this for things like dy ds is equal to f of y. And you can also use it for dy ds is equal to g of t. Okay. It actually makes it easier. You only have to deal with one of those integrations. S, thank you. Thank you. I guess the reason I said t here is because this is the one that's going to be useful to us as, like, for example, if you have dx dt is equal to 3t squared plus 5t minus 10. You can solve it this way. Okay, so, and that's going to come up a lot because, so let me do an example. So let's say that what we know is that the x component of the velocity is, I'll use what I just did, 3t squared plus 5t minus 10, okay? And let's say that at time equals 0, x is equal to 3. So find the x component of the position. This a lot of times will also just be given as x, you know. Okay, so what this says is the definition of the x component of velocity is the time derivative of the x position, okay? And that's equal to 3t squared plus 5t minus 10. And so dx is equal to 3t squared plus 5t minus 10 dt. And now you can integrate both sides. And you get that x is equal to t cubed plus 5t squared over 2 minus 10t plus your one constant of integration. And now we can use the boundary condition that says set t equal to 0 and set x equal to 3. So 3 is equal to 0 cubed plus 5 times 0 squared over 2 minus 10 times 0 plus c. So c is equal to 3. And so your function x is equal to t cubed plus 5t squared over 2 minus 10t plus 3. Okay, any questions about that? Okay, what about higher order derivatives? Well, just do them in steps, you know. So, for example, let's say that we know that the acceleration, well, let's do this and derive the equations of motion that you're used to for constant acceleration, okay? So let's say that the acceleration vector is equal to 0, negative 9.81. Okay, and let's say that we're given that when time is equal to 0, the velocity vector is v0x, v0y. Those are constants. And also at time equals 0, the position vector is p0x, p0y. And we want to find the position vector as a function of time. Okay. Well, remember that the acceleration is the second time derivative of the position. So we're going to do a step to get to the velocity, a step to get from the velocity to the position. And since this is a vector problem, and we have 2 components per vector, this really is 4 integrations that we're going to have to do. Okay, 2 for the x component and 2 for the y component. Do we have the 4 boundary conditions we need? Yeah, we have the 2 x boundary conditions and we have the 2 y boundary conditions. Okay, so let's first do I guess I'll do all the x's first. So we're given that the second time derivative of the position, you could write this as let's do it like this. So the second time derivative of px with respect to time is equal to 0. So I'm going to write this or think of it as d dt of px dot. Okay, that's how I'm thinking of this second derivative. And this px dot is vx, by the way, too. And I'm going to say that that's equal to 0. And now I'll separate variables, and we get that d px dot is equal to 0. And we can integrate both sides. Integrating the side on the left gives you px dot, and there's a constant of integration. This one gives you 0, and so you just come up with something like this. I'm going to call it C1. Yeah?
What are we integrating with respect to on the right-hand side?
It's an integral of 0. So remember, an integral is just adding up a bunch of infinitesimal things. It's adding up a bunch of things. I mean, it's that, but the 0 makes it go away. But if you just add up, you can add up a lot of zeros and it still gives you 0, is the idea, you know? Okay, so now let's use the boundary condition, the first boundary condition. That says that, so this is equal to Vx. Our first boundary condition says when time is equal to 0, Vx is this constant V0x. So V0x is equal to C1. So now our Vx, which is equal to our Px dot, is just equal to V0x. Okay, that's our first step. Are you with me on that? And now we'll go to our second step. And this one says dpx dt is equal to V0x. Separate variables. Integrate both sides, and you get P sub x is equal to V0xt plus some second constant. Use the boundary condition here. The boundary condition says when time is equal to 0, P sub x is equal to this constant P0x. So Px is equal to, when time is equal to 0, this term goes away. So plus C2. And so C2 is equal to this constant P0x. And so our function Px is equal to V0xt plus P0x. Are you with me on that? So now we're going to go to the y component. And we're given that, so we have that d squared of py dt squared is equal to negative 9.81. So d py dot, or you could think of that as dvy, it's the same thing, is equal to negative 9.81 dt. Integrate both sides. You get that py dot is equal to negative 9.81 t plus C3. The boundary condition says V0y is equal to 0 plus C3. So our function py dot, which is the same thing as the y component of the velocity, is equal to negative 9.81 plus V0y. And then the last step is, so dpy dt is equal to negative 9.81 plus V0y. Remember, this is just a constant, this V0y. So separate variables, dpy is equal to I am missing a T. Yeah, thank you. Thank you. Negative 9.81 T plus V0Y dt integrate both sides, and you get that Py is equal to negative 4.905 T squared plus V0Y T plus C4. The boundary condition says when time is equal to 0, Py is this constant P0y. And so Py is equal to negative 4.905 T squared plus V0YT plus P0Y. And then if you want to put it all together, that means that the position vector as a function of time is equal to V0xt plus P0x. And then the y component is negative 4.905 T squared plus V0YT plus P0Y. And you might have used different constant names or whatever, but in physics 1, you use these equations all the time for calculating the position of an object with a constant acceleration. Well, in this case, a free fall thing with y pointing up. Okay? Anybody, I hope I didn't go too fast through the names of the constants and everything to get you confused, but I think probably in physics 1 you did a derivation like that. You probably just did it by integrating, but you can think of integrating as just a simple form of separation of variables. Okay, and remember those boundary conditions. So here are the most important derivative relationships in this class. Okay, so the first one is that the velocity vector is the time derivative of the position vector. The second one is that the acceleration vector is the time derivative of the velocity vector. And that means that it's the second time derivative of the position vector. And the third one is, my guess is that in your Physics 1 class, when you used angular velocities and angular accelerations, you used those rotating about a single axis, like motion in a plane, right? Did any of you do like three-dimensional angular velocities and angular accelerations? Okay, well, in 2 dimensions, you get a good idea of what angular velocity and angular acceleration are. They're easier to picture. But of course, you can have something rotating all cattywampus compared to the XY plane, you know. And so generally, the angular velocity and the angular acceleration are 3-dimensional vectors. And so the angular acceleration vector, alpha, is the time derivative of the angular velocity vector. Okay, so pretty much all of the differential equations that you'll have to deal with in this class will come from those 3 relationships. And when we start doing quizzes, this is definitely going to show up on at least one quiz at some point. Okay. Like if somebody at the university or whatever, a professor asked you what you learned in dynamics and you recited this, they'd be happy enough with what you learned.
Does that mean we all pass?
But I'm meaner than them. Okay, well, that's all for today. And then, so we'll get into some real dynamics on Friday. Yes?
That very first example, I've been looking at it the whole class, and I have no idea how to solve it. The one was like the second derivative of y squared to x, and then 10 dy dx dy dx.
Yeah.
You just lose.
No, I put in also, basically I just put in what I thought of as an ugly ordinary differential equation. You can tell that it's ordinary. Let's see, this one? Yeah, you can tell that it's ordinary, but then you start trying to classify it into for the people who've taken differential equations, you start thinking like, okay, is it linear? Can I work with that? Can I complete the square? Can I? Yeah, I just wrote down what looked ugly, so I don't know that there's any clear way to solve it. I've never thought of solving it. Yeah, it's supposed to look hard, but you're supposed to be able to say, okay, I can identify that there's one independent variable. That means this is an ordinary differential equation. And so if I'm going to look at techniques for solving it, I'm going to be thinking of ordinary differential equations. Yeah. To be honest, so like when you take differential equations, you learn 150 methods. That's, I don't know, maybe you learn 25 methods or something, you know, I don't know how many. But once you're 50, I mean, even once you're 25 and just a couple years out of the class, there's only a couple that you're going to really remember. And if the first couple you try don't work, the main ones, you would try separation of variables. You would look to see if you could do complete the square, complete the derivative thing. Those are probably the only 2 things that I would tend to try before I'm just like, I'm going to solve it numerically and just see what the shape is, you know. And the way you solving it numerically is actually pretty easy. It's pretty easy. I mean, you haven't seen how to do it, so it's not easy for you, but with a couple of lines of code, you could write a program that would plot out what the solution looks like, even if it was hard to get an exact solution for it. So, okay, that's all.